Good morning, everyone. Today it's my pleasure to present to you joint work we did with Graz University of Technology on so-called mobile private contact discovery. First, to get you up to speed, what is actually mobile contact discovery? Well, when you install a messaging application on your smartphone, say WhatsApp, one of the first things that happens is that the app checks which of the contacts in your address book are connected to the service as well. For this, it could of course simply tell the service provider which contacts are in your address book, and the service provider then lets you know which of these contacts are using the service. This brings me actually to the first point of my agenda for this talk. We will look at how mobile contact discovery is currently handled in practice and why there are some severe privacy issues. As a privacy-preserving alternative, we then suggest to deploy so-called unbalanced private set intersection protocols. And since there are quite some demanding performance requirements, I will tell you how we tweaked all the necessary building blocks to get great performance even at a large scale. And finally, I want to show you the benefits we can get from writing native code for secure computation protocols, not only for the server side, but also for modern mobile platforms. Now, regarding privacy concerns in mobile contact discovery, you have to be aware that the trivial procedure I outlined in the beginning basically leaks your entire social graph. Now, you might say, who cares? I'm just a boring PhD student. But imagine, for example, you're a journalist and are interacting with confidential sources and impactful whistleblowers. The service provider or any kind of agency monitoring that service might find such information very interesting, to say the least. So our contribution when it comes to examining and improving the current situations are as follows. First, we performed a survey on secure mobile messaging applications, showing that none of them provides proper privacy protection during contact discovery. Therefore, we optimized OPRF-based unbalanced private set intersection protocols with Cuckoo filter compression, novel OT precomputation techniques, and a more efficient PRF, while even providing security against malicious clients, which is very important in mobile contact discovery, since in principle, every client could run a modified version of the messaging application. And we also implemented these protocols in native C, C++, utilizing new ARM v8 instruction sets for hardware-accelerated crypto and vector operations that give us a 1,000 times faster garbled circuit evaluation. And when putting these implementations into the Signal Android client and performing large-scale benchmarks, we get that even for a database with more than 250 million users, the online phase of our protocols on a real LTE connection takes only about 5 seconds. Regarding the survey, we looked at mobile messaging applications that are secure in the sense that they provide end-to-end encryption, and checked using different analysis techniques how they perform contact discovery. Here are the results. As you can see, many of them actually use the trivial solution I outlined in the beginning. Here, for example, what WhatsApp says in its legal info: you provide us, all in accordance with applicable laws, the phone numbers of WhatsApp users and your other contacts in your mobile address book on a regular basis. The best thing some of the apps do is to use a naive hashing-based protocol where the client only sends hashes of the phone numbers to the service provider. Unfortunately, this can be assumed to be almost as insecure because such hashes are vulnerable to brute force and dictionary attacks due to the low entropy in phone numbers. As an alternative to these insecure methods, we propose to deploy private set intersection protocols, PSI in short. In general, PSI protocols are cryptographic protocols with provable security that allow two parties to compute the intersection of their input sets such that nothing but the actual intersection is revealed. The problem with most PSI protocols in the context of mobile contact discovery is, however, that their communication complexity in the online phase of the protocol, which is the phase where you actually compute the intersection, depends linearly on the size of both input sets, which is a kind of a showstopper considering that in mobile contact discovery, the server database can be expected to have millions or even billions of entries, whereas the client can be assumed to have, let's say, around 1,000 contacts only. Luckily, there are also so-called unbalanced PSI protocols that are designed specifically for the use case where one input set is much larger than the other one. And these protocols then have an online communication complexity that is only linear in the size of the client input set, and they shift the major communication complexity to a setup phase that can be run at an arbitrary point in time before the actual computation, and usually is a one-time cost. When it comes to related work in that area, we can see three protocol families. First, there are protocols based on fully homomorphic encryption that have the lowest communication. However, when running them at the scale we consider in this paper, the service provider would have to pay for around 30 million core hours every single day, which is kind of expensive. Then there's a protocol that combines PSI with private information retrieval protocols. However, they need to assume multiple non-colluding server, where in the two-server version, an external server requires a full copy of the user database, which we would like to avoid. And finally, there's a work by Kiss et al. That brings multiple existing secure two-party PSI protocols in a so-called precomputation form that allows these protocols to act as unbalanced PSI protocols. Some of these protocols are based purely on public key crypto, and some are based on oblivious pseudo-random function evaluations. From all these protocols, we closer looked at two that can easily be made secure against malicious clients simply by using malicious secure oblivious transfer. One of these protocols obliviously evaluates the now wrangled PRF, and the other one evaluates garbled AES circuits. And the reason why these protocols can easily be secured against malicious clients is because the only messages the client send in these protocols are those for oblivious transfer. To give you an idea how both selected protocols work, let's quickly go through the different phases. First, we have a base phase that is completely independent of any input and consists mostly of oblivious transfer precomputation, and the server also generates a secret key. In the version where we want to evaluate garbled circuits, the server also builds and transfers these garbled circuits. Then in the setup phase, the server encrypts all contacts in its database and puts them in a probabilistic data structure for efficient membership testing, which we instantiate in this work with a so-called Cuckoo filter. This Cuckoo filter is then transferred to and stored by the client. And finally, in the online phase, client and server engage in OPRF evaluations, where the client obliviously obtains encryptions of its address book entries under the server's secret key, which it then can check against the Cuckoo filter. So we took the mentioned OPRF-based PSI protocols and looked at every single building block to optimize performance. I now want to quickly highlight two optimizations we did on the protocol level that might also be interesting for other application areas. The first optimization is a simple yet effective compression technique for Cuckoo filters to represent the server database even more efficiently. If you don't know Cuckoo filters, they are basically a very nice drop-in replacement for the well-known Plume filters, since they are more efficient and you can, for example, easily remove elements from the filter. The main difference to Plume filters from a data structure point of view is that each bucket may store multiple entries, and instead of single bits, we store small hash values, so-called fingerprints or tags. And for some reason, all previous works always transferred all bits for all buckets, whether they are actually filled or not. Instead, we suggest in the simplest version to split the Cuckoo filter into a bitmap indicating which bucket positions are filled and a tag list containing the actual content. And this gives you a compression ratio that roughly equals the load factor of the Cuckoo filter. And since in practice you would never distribute a fully loaded filter because you would expect a lot of new users to register later on, this gives quite some nice improvements. In the paper, we also describe how to set the Cuckoo filter parameters in terms of bucket size and fingerprint length properly, so the failure probability of the whole protocol becomes negligible. And we also describe how to send updates for Cuckoo filters with 4.3 times less communication than in previous work. A quick literature recommendation here. After we had these results, we saw that last year some other guys proposed a new thing which they called Morton filters, and they basically combine such compression techniques with further optimizations and are probably the thing you would use when designing new protocols. In the protocol where the OPRF is implemented with garbled circuits, we also replace the actual PRF AES with something more efficient. And the background here is that with the free XOR optimization for Yao's GC protocol, the cost matrix in circuit design shifted. We now want to have as few AND gates as possible, while we don't care so much about the number of XOR gates. And this is where LowMC comes into play. LowMC is a highly parameterizable block cipher that was specifically designed for use cases in MPC and FHE applications and give us the possibility to tweak all these parameters according to these new metrics. We tested different parameter sets suitable for the contact discovery use case, all with 128-bit security, and chose a configuration where we require 8.2 times less communication than AES. As a next step, we implemented all protocols. And since we wanted to optimize PSI not only on the protocol, but also on the implementation level, we wrote them in native C, C++. The code is open source now, so you can feel free to play around with it. For our native implementations, we made use of new ARM v8 instruction sets in two aspects. For malicious secure OT extension protocols, we rely on libote by Peter Rendall. However, this library is heavily optimized for the x86 architecture, so we replaced all specific hardware instructions with the ARM equivalents while still maintaining compatibility to the counterpart running on the server side. And second, when implementing Yao's GC protocol, we know that the fixed key IIS garbling scheme usually gives a great performance boost due to the native AES instructions available in all halfway recent Intel CPUs. However, since the ARM v8 architecture now contains so-called cryptography extensions, we can utilize such instructions also on mobile devices, which gives in this case a speed of around 35 times compared to standard software implementations. We can also utilize the ARM Neon instruction set for efficient operations on 128-bit registers, which makes it very convenient to work with 128-bit wire labels in Yao's GC protocol. Overall, we can report 1,000 times faster garbled circuit evaluation compared to the Java implementation used in previous work. Okay, to demonstrate the practicality of our protocols, we performed some large-scale experiments. The setup looks as follows. The client is a Google Pixel 2 smartphone, and a commodity laptop acts as the PSI server. For the network, we used a real Wi-Fi connection with the shown specs, and we also used a real LTE connection. In Germany, you would probably have to declare bankruptcy after the amount of experiments we performed, but in Austria, you can do this without any problems. I don't know. When looking at the combined base and online phase for checking 1,000 contacts in the client's address book, we can see some great performance improvements, both in terms of runtimes and communication. Please notice that these axes here are in log scale. And on this slide, we compare our protocols to the respective protocols and implementations by Kiss et al. Executed in our benchmarking environment. And we choose their work for a direct comparison because it is actually the only one with an implementation of unbalanced PSI protocols on smartphones. When looking at the setup phase for a server database with more than 250 million users, we can see the positive effect of the Cuckoo filter compression, assuming a load factor of around 70% here. However, transferring about 1 gigabyte of data at some point in time, even over a Wi-Fi connection, can be seen as quite prohibitive for the real-world deployment. So in the paper, we therefore suggest multiple extensions to further reduce communication. The one I want to quickly present here is a combination with multi-server private information retrieval and works as follows. First, the main server transfers the Cuckoo filter to a second non-colluding server. And here I want to stress that the trust assumptions are not as strong as in other protocols because the Cuckoo filter contains only encrypted elements, and in the case collusion happens, the security level is still better than in the best currently deployed methods. And in the second step, the client then runs OPRF evaluations with the main server and then uses a multi-server peer lookup to check the existence of the contact in the server database. And most importantly, this way the total client-server communication is reduced to be logarithmic in the size of the server database and becomes practical even for services with more than 1 billion users. So let's conclude. Today we've seen the currently most practical protocols and implementations for mobile private contact discovery. The presented protocols are not only suitable for contact discovery, but a general purpose unbalanced PSI protocols. So therefore, they could as well be used for mobile malware detection and the discovery of leaked passwords, just to give some examples. We also think that our native implementations of Yao's GC protocol on the ARM v8 architecture can be useful for quite a lot of future secure computation applications on mobile devices. There is one thing, however, that I don't want to hide. We contacted one of the services on the survey list and asked how they see the chances for a real-world deployment of our protocols. Unfortunately, they gave us a quite demanding requirement list where the maximum amount of communication they want to spend is probably the biggest issue right now. So, and since we cannot meet these requirements yet, I can only encourage everyone in this room to look into this interesting and important research area. With this, I'd like to end, and I'm happy to take questions. Thank you.
Any questions on this, folks? Okay. I have a question. So you mentioned that you have 2 PRFs, and you may have had the result in there. I just missed it. What was the comparison between the Noor-Reingold and the garbled circuit approach?
So in our experiments, it turned out that they roughly have like equal performance. The IIS, of course, has some overhead in the base phase because we need to transfer these garbled circuits. So you might ask which one is the one to choose. I would say it's not clear. It depends on the use case. The benefit of this IIS version is, of course, that it's not only limited to like a specific private set intersection, but you can also do this generic PSI computation where you could compute an arbitrary symmetric function on top of the intersection result. So in that case, I would suggest to use the IIS or LowMC version, and otherwise they turned out to be roughly equal.
I'm sorry to ask 2 questions here, but very quickly, because I know we have limited time. Are we going to get to those requirements in the next 5 years? 2 years. I'm pushing it down. Is it possible?
I think if you don't weaken some assumptions like this, they also said they don't want to have any non-colluding servers. If you don't weaken these assumptions, I don't see it coming that fast. I mean, there are other approaches that are being explored, like using Intel SJX, which is like a technology preview of Signal, but has, of course, other shortcomings. So having this extremely strict requirement set and having all these strong assumptions, I don't see it coming that fast.
Well, still, it's big progress. So,
yeah.
All right, one more round of applause. Thank you.